5.5 Properties of Logarithms. So we're going to prove some properties, and some of them will be fairly formal, some of them are fairly informal. Most of these you should be able to do if I asked you to. So let's look at the first one. So the log a of 1 is equal to 0. If I asked you to prove that, you can start by removing the 0 and just say, well, let's see what the log a of 1 would be. You can use a definition of a log. A to the exponent of y has to be 1. And if that is true, then you can rewrite 1 as an a to the power of 0. So this is your answer to the question here. And that brings you back to the definition. And that means that the log a of 1 is always 0. It's consistent also with the fact that the log is asking you a question, which is what exponent do I need to shove on a to make it come out as 1. So you can see that 0 works because of that. So the next one, if the log a of a is always 1, how would you show that? Well, the same way. Start by introducing y as a variable on this side. Use the definition, so a to the exponent of y has to be equal to a then. The unseen exponent here is 1, so you get y equals 1. And then you can rewrite it as the log a of a is always going to be 1. So the third one, same thing. So initially replace that. And let's see what happens with this one. So again, if you use the definition, if you say a to the exponent of y has to equal a to the exponent of r, then that means y has to equal r. And you're back to what we were given, or what we were being asked to prove, and that means that you can now write this the following way. So the exponent you need to shove on a to make it come out as an a to the r has to be r. So those work very similar, and they're sort of all in the same little grouping. The fourth one here is slightly different. For this one, you could just sort of reason your way through it with the definition and definitions that we know, and it does work, but I'm going to try to show you this one actually with some numbers. And we'll see, what if I said that we were asked to solve this problem? Okay, well then the first thing that I would do is I would say, well, let's see then if we can figure out what this is. Okay, so the log 10 of 100. Do we know what the log 10 of 100 is worth? Well, let's see. That means that 10 to the exponent of y has to equal 100. And then 100 is 10 squared, so that means y equals 2. So replace this expression with a 2, and then let's see what do we get. So 10 to the power of, all of this is worth 2, and 10 squared is 100. Now if you look back at the original thing that we were looking for, which is that a log a of m is always m, did it work in this case? So when 10 is the base here and 10 is the base there, then did we get 100 as our answer? And we did. Okay, so that worked great for numbers that we know. But we should be able to prove, or we should be able to use this rule now from here on out, even if we don't know what values they would be. So for example, what I'm trying to say is this. As long as these bases match, if this is a 5, I still should know the answer to this, because in essence it's asking you this. Well, this is asking you a question. What exponent do you need to shove on 10 to make it worth 5? Well, I don't really know what that is. It's not a half, right? Because that would be the square root of 10. But it's a number. So whatever number that is, it's less than 1. If you shove it then on 10, you should get 5 back. So this does work for anything that is given to you. So as long as these bases are the same, then you know that you want to get this as your answer. Okay? Alright, next set. Let's look at the following kinds of things. So that was 4 things that we've sort of proven. So if a is the log a of m, then a to the exponent of a has to equal m. And if b is log a of n, then a to the exponent of b is equal to n. So we're starting with this, and we're going to assume that these definitions are true. So then here's number 5. We're going to see if we can figure out what you should get out of this. And to do that, we're going to plug in m and n. So if the log a of m times n is asked, then I should be able to write that as the log a of, and m is a to the exponent of a, and n is a to the exponent of b. If you have the same base, you can add exponents, so that means I actually get the log a of a to the power of a plus b. And then I think this is rule number 3, right? We just sort of proved that if the bases are the same, you should just get the exponent. So this should just be a plus b. So let's double check that. So rule 3 should be just above it. And rule 3 said if the bases are the same, you just get the exponent. In this case, the exponent is a plus b. And that leaves us with the following. It leaves us with this, that the log of a product is going to equal a plus b. And a was the log a of m. So the log of the product is the log of the first plus the log of the second thing, because b was log a of n. And that really ought to make sense. It deals with the fact that logs are exponents, right? And when we multiply like bases, what do you do with exponents? You add. So it works both with the definitions that we know and sort of with, you know, the verbal way that we look and interpret this stuff. Alright, so number 6 then would be, well, what about having a division over here? What should you get out of this? Well, let's just write that with m being a to the exponent of a, and n is a to the exponent of b. And since we're dividing here, that means we can subtract exponents. So the log a of a, and then a minus b. And then again, we're in rule 3, which says that these bases are the same. You should just get your exponents. So this is a minus b. So now let's look what we actually ended up with. So the log a of two things that you are dividing is equal to a, which is the log a of the numerator, minus the log a, and b is actually the log of the denominator. And again, that should make sense because when we divide like bases, we subtract exponents, and logs represent the exponent. Okay, so now we've proven those. And you got a couple more that we can do, I think. This is its single little brother. So we're going to say that a is defined as the log a of m again. That means that, sorry, that means that a to the exponent of a is m. So using this definition, or using that as a given, what do you get out of this thing? So this rule is slightly different than the rule previously. Rule number 4, I believe, we had, number 3, we had same basis, we just get the r. Okay. Notice here that a is not the base of the exponential that we're looking at. So what can we do with this? Well, we know that m is a to the exponent of a, right? And then we're raising that to the exponent of r on the inside. So that means that we should get multiplication here, because an exponent on top of an exponent is just the product of those. And that means you just get r times a. So what do we have then? So we started with this, the log a of m to the exponent of r equals r, which was the exponent that we had, and then a. And a was the log a of m. So the way I look at this rule means that if you have an exponent over here, you can just shove it out in the front and work with it that way. And that's really what we're doing here. So we don't, the log doesn't completely disappear. It's still there, but you know, it does make your life a little easier, especially in problems that are specifically set up to test this. Now we can go one step further here. If you didn't know this rule, if you didn't know that that's supposed to just give you r, can you use this? Can you still use this? So yes. Then hopefully maybe you do know the rule that we had over. Maybe it was rule number 1 or rule number 2. I think it was rule number 2. So what happens when you take the log a of a? That's 1. So if I look at log a of a, and that's 1, the log a of a is 1. So you get r times 1, which is just r. So notice that we have another way sort of proving, of showing that when the bases here are the same, you just get this exponent. Okay, now if you use this rule, so if you use this thinking to show that log a of a equals r, you do actually have to prove this part over here first. So this is a longer way of proving that than I did in the first one. Because you would have to prove this general rule first, and then plug this one in and use the definition that was given over here. So don't think that that's the best way to do it. It is possible. Okay. And then the last one. So the last one's a little trick that allows us to work with different logs. So we're going to say we're going to let y equals the log 3 of 8. Okay, I'm going to manipulate this for a while, and then at the end we'll draw a conclusion. So if this is true, that means that y cubed, did that backwards, didn't I? That means that the base 3 to the exponent of y has to equal 8. And then let's solve this for y. So since I'm lazy, I'm going to take the natural log on both sides. So that means that the natural log of 3 to the exponent of y is the natural log of 8. Then using the rule that we just sort of developed over here, so minus this one, right? So this was just me going a little bit further. If you have an exponent and you have some stuff over here, you can just bring the exponent out. So now you can see hopefully why I said this will make your life a little easier in some cases. So the y can come down. The exponent is just multiplying the natural log. And that means that y will be the natural log of 8 divided by the natural log of 3. Now you might be wondering, why would you need this? If I gave you this and you had an older calculator, then there's no way to figure out what value y is. So right now I don't know what y is worth. But if I look over here, it says y is actually the natural log of 8 divided by the natural log of 3. So what this means that you can use a calculator to find what the log 3 of 8 is worth. You can't plug that in the calculator, but you can find out what the log 3 of 8 is worth by saying, well, that is the same as the natural log of 8 divided by the natural log of 3. Okay, and that can go in the calculator. What we sort of name this rule is then this allows you to rewrite any log in a different base, and that's useful because the calculator only has really two bases, okay, natural logs or the common logs. So would this have worked if I had asked you to solve this? Would this work also if you use the common log? So 3 to the exponent of y is equal 8. Take the common log on both sides, so that means you get y is the log, not y equals. I'm ahead of my mind again. I do y times the log 3 equals the log of 8. So yes, you would get y equals the log 8 divided by the log of 3. So that allows you to rewrite any log in a format that you can put in the calculator, because this one you can plug in, keeping in mind that the base that we're using here is, if I just write log, this is a base 10, right? That's a base 10, and again that one we have in the calculator. So if you're given a log with a base a of a number b, you can write this as y equals the common log of any base, so any base that you want, of b divided by the log of whatever base you desire, and then you take it of a. So the b goes in the top. Where do we see that over here? So for example here, if I look at log 3 of 8, the 8 went to the top, right? So the b goes to the top. The 3 is already below the 8, so the 3 is the one that goes below, so that's the one you divide for. And usually the two that we use here then would be, well, it's either ln b divided by ln a if we use the natural log, or it's just the log of b divided by the log of a if we use the common log. Okay. Alright, so that's a bunch of things that you should be able to prove. And I think that's it for now. The next clip I'm going to do is I'm going to show you some examples.